Okay, the ideal gas law. We've discussed several of the simple gas laws. There's actually a couple of others. But all of these can be combined into one single law. It's good to understand how this happens, but it's not critical. So volume is proportional to 1 over the pressure. Volume is proportional to the temperature. Volume is proportional to the amount of gas in moles. So we can put that together like this and say the volume is proportional directly to the number of moles and the temperature and to the reciprocal of the pressure. If you have a proportionality and you want to make it into an equality, you throw a constant in there. So we get V equals nRT over P. If we cross multiply it and get rid of the fractions, we get PV equals nRT. So this is what we call the ideal gas law. It describes the behavior of an ideal gas. And we'll talk later about what the difference between a real gas and an ideal gas is. So that constant R is called the ideal gas constant because it's the constant for the ideal gas law. That constant can be expressed in different units. And so when you change the units, you change the number. But we're going to use this value right here. We're going to use atmospheres for pressure and liters for volume because those are common units that we use. So R is 0.08206. And the units look really messy. Liter atmospheres per mole Kelvin. But the reason they are like that is so that the units will cancel out when we do a calculation. If you rearrange this for R equals PV over NT. And so the units would be atmospheres, liters, or liter atmospheres, mole, and Kelvin. So that's how it gets those odd units. You should know this number. You should memorize that number, and especially the units. It may be given to you on a test, but you're going to be using it a lot, and you'll save a lot of time if you memorize it. And you should also memorize the ideal gas law. From the ideal gas law, we can get Boyle's law, Charles' law, and Avogadro's law. So this is the flowchart diagrammy thing from your textbook. I don't actually find that very useful, but I do want to show you something that I do find useful. No, that's not what I wanted. Or this one. This one, that's what I want. Okay. So we remember PV equals nRT. Sometimes people call it PivNert, because that's, if you tried to pronounce it, PV equals nRT. PivNert. Well, if we take one PivNert and divide it by another PivNert, since PV is equal to nRT, we are dividing both sides of this equation by the same thing, right? So let's put subscripts of 1 on those variables in the numerator and subscripts of 2 in the denominator. I didn't put a subscript on R because it's a constant and it's not going to change. If R is a constant, then we can say it cancels out. Right? Because R over R, 0.08206 over 0.08206, cancels out to be 1, right? So I'm going to get rid of R. So there we have an equation that relates all 4 of the variables when something's changing. So you can use that equation to solve any of these problems where you need a simple gas law. So let's say we have, we just did Avogadro's law. Let's say we have volume and amount of gas changing, but the pressure is constant and the temperature is constant. If the pressure is constant, then P1 is equal to P2, right? It's not changing. So we could get rid of that. Oops, I thought that was the eraser. P1 over P2, because it's not changing, it's the same, it cancels out. If the temperature is the same, then the temperature cancels out because T1 is equal to T2. So what do we have left? Well, we have something that kind of looks like Avogadro's law. To make it look exactly like Avogadro's law, we just need to switch those two guys. V1 over N1 equals V2 over N2, and there's Avogadro's law. It's hiding in there. You just have to peel some layers away and bang, there it is. Now, do you have to rearrange it like this before you use it? No. You can just use this version, rearrange it, solve for whatever variable you need, and go on your merry way. You can do that with any of them. Okay, any questions? Take one ideal gas law and divide by the other. So you're going to need to know how to do Charles' law, Boyle's law, Avogadro's law problems. So if you're just really, really good at memorizing things and you want to memorize all those equations, that's great, go right ahead. Or you can take this approach, just memorize the ideal gas law, divide one by the other, cross off anything that's not changing, and you've got the equation that you need. So let's do an ideal gas law problem. An 8.50 liter tire contains 0.552 moles of gas at a temperature of 305 Kelvin. What's the pressure in atmospheres and PSI of the gas in the tire? So we could recognize that this is an ideal gas law problem, right? Because it says ideal gas law right up there. But what if it didn't have that title on it and we were taking a test and we were stressed out and we're like, I don't know what to do? Make a table. You can take that same approach, make a table. So let's do that. So we make a table like before, ones and twos. We start putting the numbers in. 8.50 liters. Okay, well that's a volume, because liter is a unit of volume. 0.552 moles. So, what did I do? There we go. That's N, because N is amount of gas in moles. Oh, 305 Kelvin. I guess we need to extend this. 305 Kelvin. Do we need to convert that temperature? No, because it's already in Kelvin. That was like a birthday present right there. Oh, we ran out of numbers. There's only one row in my table. Nothing's changing. That's why there's only one row. We just have one set of conditions. Using the simple gas law, something was always changing. So, is this table a waste of time? No, we just don't need the second row. What we've done here is we've identified our numbers. So since nothing's changing, the law we need, the equation, is PV-NRT, PV equals nRT. What are we trying to find? P. What is the pressure? So I need to rearrange this for pressure. So I'll divide both sides by volume. And I get P equals nRT over V. So pressure equals nRT over V. Okay, so what's N? Oh, we've got that labeled right there, 0.552 moles. And R is something we should memorize. It's a constant, 0.08206 liters times atmospheres divided by moles times Kelvin. Temperature is 305 Kelvin. And we want to divide that whole mess by the volume, which is 8.50 liters. Always write the units in your problems. This line right here, this is the minimum of showing your work. Writing out the rearranged equation and then showing the values with the units that you plug into there. Always check the units before you do any calculating. So let's see what we can cancel out here. Moles cancel moles, liters cancel liters, and Kelvin cancels Kelvin. I'm left with a unit of atmospheres, which is a unit of pressure, so that's a good sign. It doesn't prove anything, but it's encouraging. 0.552 times 0.08206 times 305 divided by 8.5. And you'll notice that most of these numbers, again, have 3 significant figures. The ideal gas constant here is not exact, but it's given to 4 significant figures, so that shouldn't limit our answer. So I'm going to end up with 1.62, there's my third sig fig, 53 atmospheres. This question is asking for 2 answers, a pressure in atmospheres and a pressure in PSI. So that would be 1.63 atmospheres. That's one answer. One of my pet peeves is when a question asks for more than one answer and students only give part of it. And that's the sort of thing that'll mess you up on like job applications and stuff too. They ask you a series, a bunch of things in one sentence question and you leave stuff out. That'll get your application thrown out right away because they're just looking for excuses. They've got piles of applications to look at, right? So they're looking for anything to just weed out some people. You don't want to be in that group. The other answer needs to be PSI. So 1.6253. I want to use the unrounded value here so that I don't have any rounding errors. I need to convert this to PSI. This can be done in one step. So you go back to the table of pressure relationships. You have PSI on top, atmospheres on the bottom, so the units work out. It's 1 atmosphere. The book gives you 14.7. It's really 14.69. It's better to have more sig figs than fewer. So I've got 1.6253 times 14.69, and this will also have 3 significant figures, 23.876 PSI, and then I'll round that 23.9 PSI, pounds per square inch. Any questions? This is a very straightforward ideal gas law problem. The quantities that we're given here all have the correct unit. We don't have to convert units beforehand. The only little twist is it asks you to also give the pressure in PSI. Let's do another one. What volume does 0.556 moles of gas occupy at a pressure of 715 millimeters of mercury and a temperature of 58 degrees Celsius? So this is also an ideal gas law problem. And without the title, if you read through this, you may recognize that it's not talking about anything changing. And it doesn't give you doubles of any of the quantities. You've got one volume, one pressure, one temperature. So you can make a table, or you can just write down the numbers and identify what they are. So 0.556 moles. Well, the variable we use for amount of gas in moles is N. So I'm just going to label that. And then I've got 715 millimeters of mercury. And that's a pressure unit. It also tells me it's the pressure. And then the temperature is 58 degrees Celsius. So that's T. And they're asking us to find the volume. So volume equals question mark. So we need the ideal gas law, PV equals nRT. This time we're solving for V, so we'll divide both sides by P. If you have trouble rearranging equations, please get some help. I can help you, or you could find somebody else. But that's going to be a problem. It's going to be a big problem if you can't do that. So nRT, so let's just go down here and start plugging things in. N is amount of gas in moles, 0.556 moles. R is 0.08206. And those crazy units, liter atmospheres per mole Kelvin. And the temperature, what is this degrees Celsius? Does that make you say, hey, something's wrong? Yeah. We can't use degrees Celsius in any gas calculations. That always has to be Kelvin, regardless of what kind of a problem it is. So we better convert that to Kelvin. So we're going to add 273. 58 plus 273. And if you like doing math in your head, go ahead and do it in your head, but then check it with your calculator. Okay, so there's the temperature. 331 Kelvin. And then I need to divide by the pressure. Look at the units. The units in the ideal gas constant tell us what the units on the other things have to be. So we've got liters, that's going to be our volume. The pressure needs to be in atmospheres. They gave it to us in millimeters of mercury, so we have to convert. And this is a conversion that you're going to have to do a lot. So we want atmospheres, so we're going to divide by millimeters of mercury, so the units work out. And then this is one, it'll save you a lot of time if you memorize. 1 atmosphere is 760 millimeters of mercury. And that is an exact conversion. So that's not going to affect the number of significant figures. So 715 divided by 760. 715 has 3 significant figures, so this result has 3 significant figures, 0.940, and then I want to write down 2 extra digits to avoid rounding errors. So my pressure in the bottom is 0.94078 atmospheres. Now I can check my units. Moles cancel, atmospheres cancel, kelvins cancel. Do the math. 0.556 times 0.08206 times 331 divided by 0.94078 equals. How many significant figures should my result have? 3. All the numbers, well, not all of them, but the amount of gas in moles and the pressure both had 3 significant figures. The temperature only had 2 significant figures. But when I add 273, that becomes 3 significant figures. Because when you're adding, you can change the number of significant figures. So it should have 3 sig figs. The volume is liters. And so this would be 16.1 liters. Any questions?